So in this lecture we're going to talk about a number of different sensing and actuation principles. In terms of sensing we're going to talk about resistive sensors and capacitive sensors. In terms of actuators we're going to talk about thermal actuators, electrostatic actuators, piezoelectric actuators, or piezoelectric transducers, and magnetic actuators. So as we already said, for example, thermal actuator, with that we mean an actuator that converts thermal energy into a work output. Electrostatic actuators is a system that converts, an actuator system that converts an electrostatic energy or electrical energy into work output. Same with piezoelectric, is electric to work output, and a magnetic is to transduce a magnetic field into work output. So first, thermal actuators. First we're going to talk about thermal actuators. Thermal actuators are systems that transduce heat into motion. And this tree structure shows you all the different ways you can do that. Basically, if you have heat, you can either use thermomechanic principles or phase change. Thermomechanic principle means a pure thermal expansion. If you heat something up, it will expand. Something will also shrink. And you use that movement change to create a work output. You can also use a phase change, in which case the heat triggers a change of for example, one material phase to another, such as, for example, from a liquid to a gas, or for a solid to a liquid, or even we'll see some solid-solid phase changes and how they can be used. First, we're going to talk about thermomechanic, thermal expansion, and specifically thermal bimorphs. Thermal bimorphs are going to be the first example. What's a thermal bimorph? It's also called a bimetal. If you use metals, a bimorph is a structure, a thin structure in which two materials, material A in yellow and material B in red, are fixed together at an interface. And these two materials will typically have, they're different materials, they will have different coefficient of thermal expansion. So that means that if you heat, for example, if the thermal expansion of material B is higher than of A, then if you're going to heat the system, A is going to become a little bit bigger, but B is going to become much bigger. So you can see this structure, if it's bonded in the middle, it will be forced to curve. So B will expand more than A. The structure will adjust its geometry to allow one material to expand more than the other. And if you have two thin flat plates and you make them bend, they will form a perfect spherical structure with a curvature radius that is expressed by this formula. An example of bimetallic actuators, not in MEMS but in your daily life, is an electronic safety switch for cooking plates, in which you have the current go from an input terminal through a metallic bimorph, to an output terminal. And this bimorph here, for example, if the cooker becomes more than 100 degrees, for example, you're trying to boil water, if all the water would boil away, so then of course you get in a dangerous situation, because the temperatures can start rising uncontrolled and maybe create a fire. So for example, if the temperature is above, say, 110 degrees, this bimetal will move so much that automatically this connection here will be broken. So it is an inherently safety mechanism. If the temperature gets too high, the current loop is broken, you don't have current anymore, and the system can't further heat. An example of a bimorph in MEMS is shown here. This is an example of a system put on an endoscope for in vivo optical coherence tomography. What does that mean? Endoscope is a very thin instrument that is used in for medical purposes, and it's put, for example, in the vein or in the intestines to make measurements or to see or to manipulate something there. And what these people have built here is that they have, at the end, they have put an imaging system. So they have put in the endoscope, there's a fiber, and the fiber shines light and collects light at the same time, and it shines light on a little mirror that is suspended, a micro mirror that's only 1 square millimeters large, And this micro mirror is scanning both in the X direction and in the Y direction. So it makes a scanning movement. So basically what happens is that the light of the fiber goes in and is also scanned in an XY direction. So you're actually looking at a specific patch of whatever it is you want to look at. And at the same time, you record that also. So the light is recorded, and this information that you record, so in a computer, they can then reconstitute the entire image by putting all the scanning points in the right order. Here you see how the schematic. This is a picture of how it looks like in illustration. This is the schematic where you see the fiber and the and the mirror, and how the mirror reflects the light to a focal point. So let's focus just on the mirror system. This is how it looks like. You have a little mirror plate, 1 by 1 millimeter, and it's suspended by 4 actuators, and it's these 4 actuators that will make the plate tilt. This is the picture of one such an actuator. It consists of 1 bimorph and a leg, another bimorph and a leg, and a third bimorph. And then you see that the mirror, so there's 4 of these leg systems, and the mirror is then flat in the non-actuated state. And here you can actually see how it looks like, this flat mirror plate with the 4 actuators. And now if you start actuating these in the right order, you can make this whole system tilt. So far, thermal bimorphs. Another type of thermal actuator or mechanic is the monomaterial thermal stress. Here we will relay on the expansion of only one material. So in a bimorph you have the 2 materials that expand at a different rate. Now we are only going to have one material that is expanding. And here you see an example of such a system. It consists of a U-shaped beam to which you send a current. So if I send a current through a small slender structure, it's the resistance will make sure that it heats up. So what happens is that this U-shaped beam will start heating up. Now we see that the top leg of this U-shaped beam is thinner than the bottom leg. That means that this, if the beam is thinner, it will have a higher electrical resistance, and therefore, for a fixed current going through it, this thin leg will heat up more than the bottom leg here. So I get a hot leg and a not so hot leg, and therefore the hottest leg will expand more than the bottom leg, and what you'll see is that the whole structure will start shifting and moving downwards. Here you can see a top picture of such a structure. It is fabricated in a silicon surface micromachining. So this is a polysilicon structure on top of a silicon substrate. Where you can see the hot thin arm and the cold thin arm. Yet another example of a monomaterial thermomechanical actuator is a type of actuator that has been developed at KTH, at MST. It is a so-called Vgroove actuator, and the principle is the following. We used a piece of silicon and etched a V-groove in it, and then we filled this V-groove with polyimide. Polyimide is a polymer, it's a plastic, and when in the uncured state, it is a liquid, so it's just monomer. So you pour in the liquid, and then you cure it, this material, and while curing, this liquid polymerizes, and the polymerization means that it will shrink. Now the material will try to shrink isotropically, but you can see that the distance here at the top is larger than the distance in the bottom. So if the shrinkage percentage is the same everywhere, you will see that relatively the shrinkage is the same, but absolutely the absolute shrinkage will differ, because the long will shrink, for example, 50%, that becomes this long. The short will shrink 50% and becomes this long. So the longest side will shrink absolutely more than the shortest side. And what happens basically, this shrinking forces the whole structure to bend. See? So instead of having a flat structure, going to a banded structure. Typically, one V-groove creates a bending of around 30 degrees. And here you can see pictures of such a structure. We have actually, this was a silicon plate with 1, 2, 3 V-grooves, each of them filled with polyimide and then cured. And what happens with the curing, because this plate has been free-etched, this whole structure during the curing completely bends out of plane. See that? So you see you have 3, it's about 30 degrees, so you have an almost 90-degree plate standing up. 3 V-grooves, this is 5 V-grooves and 7 V-grooves, the whole structure bends down on itself. So, is this an actuator? No, this is not an actuator. This is just an out-of-plane structure. But to make it actuate, actually, I will have to make it move. And how do I do that? Well, what I can do is integrate, you cannot see that here, but integrate it underneath this polyimide are aluminum heaters. Now what happens is that after manufacturing, this thing is standing up, but once you start actuating, you're heating up the polyimide will expand when you heat it up, and it will expand more than the silicon, and therefore the whole V will start expanding a little bit again. So when you heat it, so you see the static angle in blue, and then the dynamic angle when you heat it, it will move back to position here. So I can actually make this little plate flip up and down like this while heating and cooling. In our lab, we have used this principle to build conveyor belts and micro conveyor belts and walking micro robots. And I have uploaded 2 videos. The first video is just to show the mechanism of how you can use this plate as a leg of a walking micro robot. So you have 4 legs. You can see how this structure can walk. And another video is the actual video shootage where you first see it being used as a conveyor and then as a walking micro robot carrying a lot of load. You will also see, for example, how the measurement is done when the structure is moving. We use the laser, stand the laser on it, and then it works as a mirror, and the laser is deflected, so you will see the laser spot moving up and down. It can also work as a moving micro mirror. We did that just to characterize the actuation of the system. It's a rather long movie, 8 minutes, so feel free to watch it or not, or skip through it. It's up to you.